So it's my pleasure to introduce the first speaker of this afternoon, Bethany Marsh from the University of Leeds, who will talk about properties of tau exceptional sequences.
Thank you very much, Sibylla, and thank you very much for the invitation to speak. So I'm going to talk about some joint work with Aslak Bakke Buan, who's based at NTNU. And then there's the list of supporting funders there. Okay. So we've been investigating the properties of tau exceptional sequences and signed tau exceptional sequences. So let me start by talking a bit about that. So I'll take lambda to be a finite dimensional algebra over a field with n simple modules. Then mod lambda is the category of finite dimensional lambda modules. And then we know that a module U is tau rigid if hom tau U is 0. Hom U tau U is 0. Okay, so this was a notion introduced by Adachi, Iyama, and Drayton. And then we have the tau perpendicular category. And this was introduced by Hasso. So if we're given a tau rigid module U, we could consider the modules orthogonal to it in the sense that there's no hom from U to the module, and there's no hom from the module to tau of U. And this is quite a nice orthogonal category because it's equivalent to another module category by a result of Hasso. And if U is indecomposable, that other module category is the module category for an algebra with n-1 simple modules. And if lambda is hereditary, then this is the usual orthogonal category that was defined by Geibler and Lenzing, so it goes back much earlier. Okay, so what is a tau exceptional sequence? This is a sequence U1 up to UR of modules, and UR is an indecomposable tau rigid module. And then the first part of the sequence is a tau exceptional sequence in J of UR in this orthogonal category. So it's a recursive definition. And because the number of simples goes down at each stage, the longest length it could be is n. R must be at most n. So if R is equal to n, it's said to be complete. And if lambda is a hereditary algebra, a path algebra, then a tau exceptional sequence is the same thing as an exceptional sequence in the classical sense. So Crawley-Bervey and Dringall. So these are the sequences we're investigating. And I guess they give some idea of the structure of the category that we're working with. So the first question we've looked at is unique completion. So, and for that, we need to assume that the algebra is tau tilting finite. So it only has a finite number of indecomposable tau rigid modules. And then if you've got two complete tau exceptional sequences and the entries are the same except in one place, possibly, then they must actually be the same. So that's the first result. And the motivation for this is it was already known for exceptional sequences over hereditary algebras by results of Crawley-Bervey and Ringel. So one would hope that a nice generalization like this would still have the same properties. And so we conjecture that this result holds for all finite dimensional algebras, but our proof needs the tau tilting finite assumption. Okay, and the second result is, well, in the hereditary case, there's a braid action that's already in Crawley-Bervey and Dringall. So there's an action of the braid group on tau exceptional sequences, and that's always been our motivation from the start, is to try to find such actions in this general context. And it's quite difficult, and I'll explain what we can do next. And for this, I need to talk about signed tau exceptional sequences. So here the definition's the same, except that if UR is projective, it can be tagged. or not tagged. So and this has to be done carefully. So when you go down to UR minus 1, it has to be projective in J of UR. So it's relatively projective. And if that's so, then it can be tagged, and so on and so forth as you go through. And in fact, for the hereditary case, this definition was introduced by Igusa and Todorov. So we've generalized that to the non-hereditary case. Okay, so to get some kind of braid action, I need to talk about support tau rigid objects. So we take the module category and its shift in the derived category, and that's C of mod lambda. And if W is some subcategory of mod lambda, we set CW to be W plus its shift. And this is a convenient place to consider tau rigid pairs or support tau rigid objects. So we can think of a support tau rigid object, instead of being a pair consisting of a projective and a module, it's a module plus the shift of a projective. So that's quite a convenient way to do it. Okay, so it's a module plus a shift of a projective. The module must be tau rigid. The projective is projective, and there's no hom from the projective to the module. And if the total number of summands, so this is this rank, if the total number of indecomposable direct summands in both M and P added together is N, then it's support tau tilting. And M might have some projective summands that also could be in P, and they're counted twice if that's the case. And then an ordered support tau tilting object is a support tau tilting object whose indecomposable direct summands have been linearly ordered. Okay, and the other ingredient we need is this Hasse reduction, and there's a refinement of it, which are these bijections here. So essentially, you're reducing to a lower case. So you could take the indecomposable objects X in ind CW, so for which X plus U is support tau rigid, but where X is not 0. And we can essentially get rid of the U. We can go down to the orthogonal category of U, and there we've got the objects in CJW of U, for which X is support tau rigid in CJW of U. So it's a way of passing between support tau rigid objects in a subcategory W and going down to a perpendicular subcategory inside it. That's the basic idea there. It's quite a technical definition. I don't want to go into too many details, but that's what those bijections are doing. So in previous work, we've written down these bijections. So here we've got a bijection between the complete sine tau exceptional sequences at the bottom there and ordered support tau tilting objects. Okay, so we're interested in the lower thing. So why is this helpful? Why is the bijection to the upper thing helpful? Well, the upper thing are just ordered objects. So symmetric group acts on them just by reordering them. So just by commuting the object, the summands.
I think you have about a minute left.
Okay, yeah, thank you. So we're almost there. So we've got the symmetric group acting by reordering the summand. So the symmetric group acts on the complete sine tau exceptional sequences as well. So we can ask, what is there an explicit description of that action? And that's what the main result does. So so if you've got a sine tau exceptional sequence, this S is A1 up to AN, we can permute two of the entries in it, but we have to apply these reduction maps in order to do it. So it's different from the hereditary case where one of them stays the same. In this case, you actually have to change both of them, and you have to apply these reduction maps, and then you get another signed tau exceptional sequence. So this gives an action of the symmetric group, and therefore of the braid group, because the symmetric group is a quotient. So this is some kind of analog of a braid action in this tau exceptional case, but it is not. It is highly non-transitive because it's just reordering each support tau tilting object. It can't take one object to another one, so they'll have many orbits. So it's still a question whether there could be some kind of transitive action. The last slide says, in a certain sense, there isn't, but there are other senses available, possibly. So, okay, thank you very much.